Thank you all for your patience, especially those on the internet, because I know this whole thing's been a wild and crazy experiment. Okay, last talk of the day. Once again, thank you all for coming and participating. I really appreciate everyone in the room right now and anyone who's watching online for giving us some views, and hopefully you find this talk interesting. So let me go ahead and dive right into it. This talk is about cabin sequestering, which is probably the most innovative culturing technique that has come about in almost the past 100 years. So you would figure, working with auger, there can't really be a whole lot you can do, and that would be right. And that's what makes this technique so innovative, is because this is the first thing that's happened in almost 100 years that's able to do all the things that all the previous techniques were just attempting to do. And now you can actually do it. It's very effective for cleaning contaminations out of cultures. And the original publication is a handy method to remove bacterial contamination from fungal cultures by Xiao and the rest of the crew. Let's go ahead and dive right into it. So why cabin sequestering? First, we have to talk about contamination. There's fungal contaminants, there's bacterial contaminants. Generally, when you're dealing with fungal contaminations, they are exogenous, meaning they are from the environment. They are then entering your sterile environment, and then you're having to weed it out of your culture. And while that can be difficult, it's even more difficult to clean up bacterial contaminations, because bacterial contaminations can be endogenous. They can be living, coexisting with your culture. And so it could be living right on that plate, right along with your culture of choice, and you'll never see it. You'll never know it's there. And then all of a sudden, when you try and make a spawn bag, or when you take your spawn bag and you put it into a substrate bag, everything just dies. And you're like, why? And then you start chasing your tail. Well, was it this? Was it that? Maybe I didn't cook my material long enough. Maybe I didn't do this long enough. And the entire time, you had a co-infection and never knew. And it can keep you stumped for months and months and months. And I've had to deal with this personally. I've been cultivating for over 10 years. And this has been a problem that I've had to face many, many, many times, all the way up until this publication came out in late 2019. And I got lucky and I found it early 2020 and have been using it ever since. And so a lot of people, in order to get rid of contamination, they'll use antibiotics. And so antibiotics are okay. The problem with antibiotics is that, one, they're generally hard to find. You got to go on some very specific websites in order to get streptomycin or penicillin or something like that. Two, you have to know the exact concentration to use with your media in order for it to be effective. If it's too low, you run a chance of creating antibiotic resistance. If it's too high, generally it just kind of ends up stunting your culture in some way, and that's not fun either. You're culturing mushrooms because you want your culture to be successful in its environment, not ineffective. So a lot of people also will use nutrient-deprived media. The issue with nutrient-deprived media is pretty obvious. The mushrooms need food to eat and grow. If you don't put food in the environment, then it doesn't grow very well. And what's also interesting is that if the mushrooms can survive not eating, guess what? So can your contaminant. So you're really not doing anything by putting it in a nutrient-deprived environment, besides maybe stunting both your culture and the contamination ever so slightly until you put it right back into a nutrient-rich environment and it starts growing again. And so because of these issues, there's been a constant search to find a technique that is cost-effective, efficient, reproducible, easy to do, something that anybody can be able to do it. And that is where cabin sequestering comes into play. And so before I get into the technique, I want to give kind of a brief little history of what's been going on, the types of techniques that have previously been used, and the shortcomings of these techniques. So first is the cold pour auger technique by J.E. Masheshik, which was published around 1934. And basically, the technique consists of taking auger, waiting until it is it's still in a slightly liquid state, not fully solidified. It's no longer hot. It's about to solidify, and you go and you pour your agar plate, and then right before it hardens, you take your culture and you jam it into the bottom center of the well. And what's supposed to happen is that even though some contamination may sprout up from the inoculation point, the hope is that your fungal culture is going to grow through the agar, maybe to the outer edge of the plate, that isn't affected by the contamination, and you can go ahead and pick up a little piece there. The obvious shortcomings with this is the subjectivity of having to deal with hot agar. If you put it in too soon, you burn your culture. You put it in too late, the agar is hard, and it doesn't work. And so that's where SS Co. et al. Developed the flip and scrape in 2001. Notice there's been almost 70 years since a new technique was developed. And so the flip and scrape is actually very, very simple. They would take their contaminated piece, their culture, and they would put it on top of the agar. They would then wait for the culture to grow through the agar to the other side, where they would then, using glass agar plates, they would flip the agar over and then take a little piece from the back. Or when using plastic plates, they would take a hot knife, cut a window in the back of the agar, or in the back of the agar plate, and then take a small piece from the back. And while this technique is effective, the whole flipping aspect makes it much more complicated, and having to deal with cutting through, using a hot knife to cut through plastic and all that, not exactly fun. And it's still not perfectly effective at removing the contamination. It's still easy, especially during the flipping process. Let's say there's some sort of mold that's already producing spores. You're then flipping this whole culture over in the hopes of collecting a clean piece on the other side. Well, when you flipped it, all those spores went poof, and now it's everywhere. So you didn't actually clean up your culture, you just made a giant mess. And so that's where NJ Kother and MJ Priest in 2009, 8 years later, developed the agar sandwich, which is not this cute little picture. I just thought this sub just looked too adorable. I had to put it in there. But it looks more like this, where you have an empty agar plate. You place your contaminated mycelia piece in the center. You then cover it with a giant cover slip of agar. You then place a plug on top of that. And the thought process is that the contaminated piece, the healthy mycelia, will eventually grow through the agar into the plug, where you can then sample this plug and be able to get a clean isolation. And while this technique is incredibly effective, it's not very resource or time efficient. You're still having to have lots of plates. You're still having to deal with giant floppy pieces of agar, which can slip out of forceps and do all sorts of crazy things. And it's just not as efficient at removing these types of contaminations and infections. And so that's where I'm going to get into the operational procedure and then the experimental procedure for this technique that was done by Xiao Shi. And so for the operational procedure, they prepared sterile media. They then created a hole, aka the cabin. They then placed the contaminated sample into the cabin and then covered it with a cover slip of agar that they deemed the roof. So you have the hole, the cabin, and then the piece on top, the roof. And then they would then incubate that sample for about 7 to 10 days. Once the mycelia started peeking out around the edge, they would then take a sample and put that onto a plate where it was then allowed to grow for 3 days, and then they would look at it and be able to see whether they can tell if there's bacterial contamination or not. And also a piece was taken and put into a liquid media where that liquid media was cultured for 3 days before going through DNA extraction and amplification for the bacterial contaminants that they had spiked into those samples to see, using gel electrophoresis, whether there was any DNA present after amplification. And this entire process was repeated in triplicate for each individual sample. So, if any of these results came up not congruent with the others, they definitely were taking note of that, and that's why everything was done in triplicate. And so in the experiment, they tested 4 MRRhizae strains, which is a very common fungi, and then 4 other plant pathogenic fungi to test, well, okay, if it can work for one strain, but will it work for other strains? And so that's why they were able to break it down into testing it that way. Bacteria they were used that to spike the samples were E. coli and Agrobacterium tumefaciens. There were 4 treatment sets that they used: cabin sequestering without antibiotics, cabin sequestering with antibiotics, antibiotic treatment alone, and subculturing without cabin sequestering or antibiotics, or as I like to affectionately call it, optical isolation, optical selection. Because you're just looking at it and saying, well, I think it looks clean. I'll go and pick that and put it onto the next plate and see what happens. The antibiotics they used were streptomycin sulfate and potassium penicillin, which at least the streptomycin is very efficient at killing both the E. coli and the Agrobacterium tumefaciens. And they use this evaluation equation, which is very simply the efficiency is equal to the number of clean colonies versus the number of total colonies times 100. So if they had 10 plates and all 10 came clean, so 10 divided by 10 is 1 times 100 equals 100%. And so that was how they were able to determine some efficiency at these different types of treatment groups at removing contamination from these cultures. And so the DNA and PCR analysis, so the hyphae was incubated in complete liquid media for 3 days. It was then extracted using the cetyl trimethylammonium bromide, or CTAB method, which is a very common method for extracting DNA from samples. Primer pairs were designed for amplifying the E. coli and the tumefaciens. And the pure cultures were used as positive controls, like pure cultures of E. coli and tumefaciens were used as positive controls. Double distilled water was used as a negative control. And that way they can see whether the DNA from the E. coli or tumefaciens was present, and also whether their experiment had some issues, because your negative controls should definitely stay negative. 30 progeny colonies were created per treatment group, and all of the DNA testing was done in triplicate. And so here are the results. For the MRRhizae test, cabin sequestering was effective. The cabin sequestering without antibiotics was effective at removing the culture 97% of the time after 1 round of treatment. Cabin sequestering with antibiotics had a 95% efficiency. The paper did note that there was no statistical difference between these 2 numbers, meaning that they are about the same, and that the antibiotic treatment alone was only 15% effective at removing contamination from cultures after 2 rounds of subculturing. And just using optical isolation, it was less than 5% effective after 2 rounds of removing these contaminations. So what that means is that if you're just picking it and placing it into the next plate, hoping that there's no contamination that you're carrying with it, you have a 95% chance that you just carried your contamination forward. And it's going to eventually get big enough and show up in your end product. What was interesting is that through the cabin sequestering, they noticed that the morphological difference in the mycelia was very, very, very different than the parent progeny. The parent progeny ended up looking not as good as the progenies that were generated through cabin sequestering. And when they repeated this experiment using these other plant pathogenic fungi, they noticed the exact same results. And so here is a picture of the MRRhizae strains that were tested. On the left, you have the original colonies, which you can clearly see have some contamination, some bacterial contamination. T1 is cabin sequestering without antibiotics. T2 is cabin sequestering with antibiotics. T3 is antibiotics alone. T4 is your optical isolation. And you can see that there's very, very little difference between T1 and T2. Sometimes T1 maybe looks a little bit better. Sometimes T2 maybe looks a little bit better. But in general, they're roughly the same. But you can clearly see that there is a distinct difference between T1 and T2 and T3, which looks good, but just not as good. You can see there's still something going on that's not quite right. And then when you look at T4, in some of them, it's just obviously contaminated. There's still goo present on the plate. And so when we're able to go and do the DNA extraction, the gel electrophoresis, O is your the original plate, T1 and T2 without antibiotics, with antibiotics, antibiotics alone, optical isolation, positive control, negative control, and then you have this little ladder over here to make sure that all the DNA that's being tested is within the same length. And you can clearly see that for the cabin sequestering, it did a very good job at removing all of the bacterial contamination. They couldn't even detect it or amplify the DNA, which means that it just wasn't there. But if you're just using antibiotics, boop, there it is. Not effective enough. If you're just using your eyes, that sure is not effective enough. And so that's where this technique really shines. And then when done with these other plant pathogenic fungi, you can see the very similar results. T1, T2 pretty much look exactly the same. T3, definitely not as good as the first set. T4, definitely not as good as the other three, and oftentimes still looks contaminated. And so I just wanted to kind of briefly talk about my own personal exploration with this technique, because I've been using this technique for a few years, and it has been a game changer. And so I've been able to use this on a lot of stuff that I've pulled out of the woods: reishi, chicken of the woods, lion's mane, oysters, you name it. I've tried it. It works for all of it. I will say, though, that certain mushrooms are more willing to give cultures from different places. So if you're trying to clone a mushroom, you can clone from the base, you can clone from the meat, you can clone from the cap, you can try and clone from, you can try and get some samples from gills or other types of tissue. For reishi mushrooms, I've gotten a lot of great samples from the pores. From chicken of the woods, I tend to get my best samples from the meat of the mushroom. From oysters, from the gills, or from the inside of the base material of the mushroom. And then lion's mane from the innermost tissue. Lion's mane being the most spongy and airy. If you're collecting woods from the wild, if you're collecting a sample from the wild and trying to culture it, I try to avoid collecting samples after it rains, because lion's mane is so spongy it absorbs a lot of water. With water comes contaminants, particularly bacteria. Bacteria is just kind of floating around. The rain puts it on the mushroom. The mushroom then, being very spongy, absorbs all of that rainwater, and then you have just a waterlogged, soaked mushroom. So, if you're going to go with lion's mane, you got to go to the deepest section that's the furthest away from the outermost area, just so you can get to a slice that hasn't been completely waterlogged in order to potentially get a good sample. And what I've noticed is that I've been able to, just like in the publication, they had a 95 to 97% effectiveness after one round. I have never really needed to do more than two. Generally, after 1 to 2 rounds, I can get a very clean culture that looks good and is doing what it's supposed to do and grows exceptionally well. And what's great is I've figured out a way, at least for, through some experimentation, to be able to run 4 of these on a single plate. How's that for multiplexing? So instead of only having to use one agar plate for one sample, now you can run 4 samples on the same plate. And so it can be very time and cost efficient. And what's great about this technique also is that because you are forcing the mycelia to have to grow through the agar, what ends up happening is when you're dealing with mushrooms, there is a very high probability that there is multiple phenotypes that are growing all at the same time. And so by forcing these phenotypes to grow through the agar, the strongest make it through first. The weakest are the ones that lag behind. So it can also really help not just with cleaning up your culture, but with genetic isolation. If you're trying to get a monoclonal genetic, a genetic that is only one strain, one phenotype, not a mix, just one thing, this is incredibly effective at giving you a head start. And I often am able to get monoclonal genetics very simply from doing 2 rounds of cabin sequestering. And so here is kind of the way that I run this technique. I'll usually start with a sample, whether it be a stock culture, spores, gills, caps, stems from mushrooms, kind of whatever I'm getting my hands on. I initially put it on a plate and I allow it to kind of fluff up. While I have been able to get some results by placing these materials directly into the cabin, I noticed that at least for spore generation and for tissue samples to revert back into secondary mycelia, it requires a high oxygen environment. It needs air. And for stock cultures that have been sitting in a fridge, they need to sit out and kind of fluff back up and come to life. And that if you go and place it immediately into a cabin, the cabin, especially once you put that lid on it, is a very high CO2 environment. There's very little oxygen. And so it's going to take a really long time, a horribly long time, in order for that mycelia to break through. So instead of taking 7 to 10 days, it can take 14 plus days. And so I always recommend going and getting something started on a plate, even if it's contaminated. And then after it kind of fluffs up, at that point, then transferring it into the cabin. And then from there, I can repeat this process if I need to again. But generally, if it's good enough, I'll then take isolations from the outer edges and I will put them on a plate, either individually or multiplexed for at a time like this. I will almost always notice that one sample grows better than the others. That one sample I then take and build out into multiple plates, and I'll notice further that one sample grows better than the other. This is my chase to find monoclonal genetics, because there may be subphenotypes that are hiding here. And so when I transfer it to their own individual plates, you'll notice that this one didn't grow as well, this one didn't grow as well, this one grew better, this one grew the best. And so this is how I can say for certain that I have monoclonal genetics. And the plate usually shows that in the morphology of the mycelia. There's no zoning, it's all the same. And so what's awesome is that I can do all of this. I can get clean plates in 1 to 2 rounds of cabin sequestering. It's great at genetic isolation. This is a great way to generate stock plates that you can use to make thousands and thousands of pounds of spawn, substrate, or mushrooms. And what's also great about it is that it's very time and resource efficient. I can go from the woods to my fruiting chamber in 2 to 6 weeks, depending upon how dirty I think the culture is. If I'm trying to go really quick, I immediately put it on here, wait 3 days, transfer it to a cabin, wait 7 days, transfer it to a secondary plate, a transfer plate, and then that transfer plate goes immediately into a spawn bag, and I'm growing mushrooms very shortly thereafter. And so it doesn't take a lot of resources, and this technique cuts down dramatically on the amount of time, especially if you're one of those people that is constantly running away from your contaminations by transferring from plate to plate to plate. It takes 7 to 10 days for each transfer. Let's say it's 6 transfers later. So now you're looking at 42 to 60 days of time that's passed, and the longest you'll have to spend is 6 weeks. So we're already way ahead of the curve if you're thinking about it that way, and we already know from the science that was done that even after you spent those 60 days and 6 plates later, there's a 95% chance it's still contaminated. So here I'm going to give like a little demonstration. You're going to have to, I put this in last minute, so you're going to have to forgive some of this. I was making some videos for Instagram to help explain this technique for people. So, you're going to have to suffer through this a little bit with me. There won't be any audio, but there should be some captions. We'll see what happens. Let me see if I can click the button. There we go. So here I'm just cleaning everything, because making sure that everything's clean is really important. I am working in front of a HEPA flow hood, and it is on. I have to say that because sometimes I forget that it's off when I make these videos. Next, I'm just kind of unwrapping everything, prepping the environment. I'm going and sterilizing all of my implements to make sure that they are in good form for the transfers. Now I'm cutting the roofs, the tops for the cabins. This is my general process. I can make about 10 roofs out of one plate. I then cut the cabin whole, and take my piece, pop it up, put it in, making sure not to really touch the sides or move it all over the plate. And then after sterilizing my forceps, I will grab a healthy piece of agar, place it over the top, lay it down gently, press the air bubbles out of it without moving the roof around, and then wrapping it up in parafilm. So when you're placing that sample in, you want to make sure that the cabin is big enough that your sample can fit in there nicely. If it has to squeeze in there, then what ends up happening is the back pressure of air that you are squeezing out of that pocket ends up pushing up on the sides, and if the piece is contaminated, you then pushed all of that contamination to the surface, where you then put this roof over the top of it that after you go and you press all the air out of it, squishes that contamination all around that roof, rendering the entire technique ineffective. And so you got to be really careful to go and very gently place it in the middle, with trying not to touch trying to touch as little as possible of the outer edges. And then when you put that roof on, to lay it down in a single motion, and then you're not moving it across the plate, you're literally just pressing any air pockets out so that it has a nice good seal, because any sort of air pockets can leave way for that contamination to continue to grow alongside your culture. And so in the next clip, I can show you how I do the 4. So that was a single, and this is the quad. So it's very much the same technique. Wrapping up, taking these agar plates, unwrapping them, sterilizing the implements, my tools, cutting the holes, cutting my cabins. Takes a second. Filling those cabins, making sure that the piece I'm putting in is slightly smaller than the hole that I've created. And then being very careful to cover it, making sure not to touch the contaminated sample as I'm placing the roof, making sure not to slide the cover slip around, that I am just pressing it into place and making sure that it has good contact before sealing it up and labeling it. Yep. And so there's actually a modified version that all the people here at home here at the festival get to see. I can pass around these plates. But my modified version, I'm able to do 4 samples at once without a secondary plate. I can do it all from one plate. So even if you were like, man, agar is expensive, I don't know if I can waste an extra plate like that. I'm going to show the camera. But you can kind of do it like this, where you cut your holes, and kind of like a plus sign, all the negative space in between, you can then cut a roof from that and be able to use that as your cover slip. And as you can see with this plate, it's colonized very well. I'm going to start passing this around. Cheers. And that's a sample of chicken of the woods that I pulled out of the woods a couple weeks ago. And so in conclusion, there was no real observable difference between cabin sequestering with and without antibiotics. So why even risk the chance of creating something that's antibiotic resistant? Why even use the antibiotics alone? Doesn't even make any sense. If the technique is effective and very efficient at removing contamination without it, then let's just not use it. So it's a lot more reliable than using antibiotics or optical isolation morphological selection. It's efficient, it's time effective, low tech, pretty cheap, especially if you only have to use a plate. You can do 4 samples on a single plate. It's pretty powerful. You know, a plate for an agar plate, which costs about $1. For $1, you can go and clean up all of your stuff. You can run multiple samples per plate. It's super reproducible, and it gives you the benefit of improving your genetics. So not only do you get the contamination out, but you let the best rise to the surface in order to give you a great chance at growing the best mushrooms that you possibly can. So in acknowledgement, I would like to thank my wife for dealing with me and being with me and pushing me to be better, and my family at CDC, Wild Heaven, and the mushroom community for continuing to support me. And big shout out to the original authors who came up with this technique. They really deserve the light here. And I will then turn this over to any questions. Thank you so much. Cheers, y'all. And unless I see something on Facebook, I think that will conclude the live stream. Thank you. Okay. Thank you so much, y'all. Yeah, cheers. Yeah. It's a lot of fun. It's a lot of fun.